So today we are going to start the refrigeration cycle, which is just opposite to the engine. So engine where we were generating the power by utilizing some heat input from high temperature source. So their heat transfer was taking place from high temperature source to the low temperature sink. Now we'll go in reverse direction when we talk about refrigeration. So the concept of Clausius, statement will come into the mind that we discussed in the second law of thermodynamics, which says that in order to make the heat transfer from low temperature side to the high temperature side, you need to expend some sort of energy over it or some sort of power on it. Then only you can transfer heat from low temperature side to the high temperature side. So refrigeration is basically a process of maintaining the temperature of a region or a space that you are selecting with as a temperature lower than the temperature of the surroundings. That is called refrigeration process. The process by which you are doing it, that is called refrigeration process. And for this process, in order to create this kind of scenario, you have to spend some work. So where you have to spend that work, you need a device, right, that can create this kind of environment, and the device is called refrigerator that we are using in day-to-day life. That is called domestic refrigerator. But in industrial application, the same thing, same concept is there for the another device that is we usually using as a vapor compression refrigeration plant, that usually we use for larger cooling effects when you are going to create in more than what we say 13.5 kilowatt of heat removal from certain space. For that purpose, we use the vapor compression refrigeration cycle. So whenever that cycle term comes to the picture, that means that plant will be operating on certain cycle. So we know the theoretical possible cycle which is having highest possible performance is Carnot cycle. So when we are defining the engine will be operating on the reversible Carnot cycle. So most appropriately we can say that. And similarly, when we are saying work producing, work absorbing devices, they will be operating on reversed Carnot cycle. So when you are reversing the direction, your work output which was going out will get reversed through the system. That means work need to be supplied to the system. So all the heat interactions which were happening earlier from high temperature source to the low temperature sink will also get reversed from low temperature sink to the high temperature source. So in order to create certain kind of environment, you need to spend some power on it in order to get the refrigerating effect or refrigeration in a closed vicinity that you have selected with. Now there are two ways, right, by which you can create the refrigeration effect. Let me start the PPT first. So this is basically 13th chapter, right, in the PKNAG book, or you can say in the sequence of your fourth unit. This is the second segment. We started with the third segment. This is the second segment of your fourth unit, the refrigeration cycle. So there are two ways by which you can produce the cooling effect. One is called cyclic way, cyclic processes. Another is called non-cyclic processes. Non-cyclic processes are those which will not reverse or they will not again repeat. Like in day-to-day life, whenever we are you might have seen that the traditional way or conventional way earlier was, or still today we are using the melting of ice. If you use the ice and if you expose it to the region where you are producing the cooling effect, what ice will do, the moment ice comes in contact with the atmospheric air, ice will melt. The moment it's going to melt, right, what it will do, it will absorb the heat from the surrounding. So it's going to absorb the heat from the surrounding. That means surrounding is your region where you are wanting your refrigeration or cooling effect. So when it's taking away heat from that region, that means region's energy is decreasing. So we will get the cooling effect in that particular region. So how it is happening? The latent heat of the ice is getting basically supplied to the surrounding. Because of that, you are getting the cooling effect. So earlier, even today's, in some of the cases, we are utilizing this method, and this method is called non-cyclic method of creating the cooling effect. So ice at 0 degree, usually it will be at 0 degree whenever taking the temperature. 0 degree, and this is a very, very minute boundary, right? 0 degree solid form ice and 0 degree liquid form, ice. The moment it's converting to liquid, right, entire latent heat is getting actually coming out, right, and actually getting absorbed within the ice. Because of that, it got melt. So it is absorbing the basically heat from the space where you are wanting the cooling effect. So this is one of the example of non-cyclic process by which you can generate the cooling effect in a closed region or space. There is another method usually we use in the food industry, right? Particularly for storing the fruits and all, that is called dry ice. There is a dry ice that we also say as solid carbon dioxide. If you expose that dry ice to the atmosphere, it will directly go from solid to vapor, right? Solid to vapor. You look at, so in between liquid phase is not present. So if we say that the at atmospheric condition, right? When we say atmospheric condition, dry ice will not be existing in the form of the solid, right? So initially it will be form of solid. The moment you expose it to the atmosphere, immediately it convert into the vapor. So when it's getting converted into the vapor, you can think of how much amount of heat it will absorb from the surroundings. So when you are needing very high rate of cooling, especially at minus 40 degree or lesser than that, right, less than minus 20 degree, you can utilize the dry ice method for creating the cooling effect. So usual range in this case is basically minus 85 degrees Celsius. So latent heat of dry ice is around 620 kilojoule per kilogram at minus 78.5 degrees Celsius. So look at the temperature at which it is absorbing the heat. So for the low temperature, creation, you can utilize the second method of non-cyclic way by utilizing the dry ice. But if we look at these two, right, so we know from this diagram, this you studied in the properties of pure substance, right? So when we are dealing with the dry ice, that will be basically that process will be happening from this side, right, and directly going to the vapor. So this two phase zone will be happening when it's just getting the phase change from solid to vapor. So it is starting from the solid line. This is the solid line, and process will start from this point. So immediately it will absorb this much amount of heat from the space where you want the cooling effect. This is a 620 kilojoule per kilogram, and finally get conversion to the vapor. So directly it goes from solid to vapor. But if you come to the ice, right, that is basically at 0 degrees Celsius. So ice will clearly show you indication of liquid. So it converts from solid to liquid. So the process will be represented somewhere here. So initially it will be a solid, right? Then it converts to the liquid by absorbing the latent heat of fusion, right, from the surrounding. So that much amount of heat it will be taking away from the region where you want the cooling effect. So in both of these, right, your refrigerant is undergoing, means we can say that is a working substance which is basically creating the cooling effect. So it is undergoing the phase change. Another thing is that uh, we are basically losing the working substance. Some of the portion of it will get lost because of the evaporation. So we cannot actually after some time, right, continuously you cannot create the cooling. So in order to produce the continuous cooling, there are waves that is called cyclic waves, where continuously refrigerant will be moving through the piping systems. Even though in this case it will undergo the phase change, but there will be no loss of mass. So mass flow rate will remain the constant throughout the system. So it will convert from liquid to vapor, then again reconvert into the vapor to liquid, but there will be no loss of mass, and that cooling will be continuous. But in this case, it will not be continuous. It all of a sudden you will get the cooling, and then after that, once your mass of your substance that you are utilizing for cooling is getting reduced, your cooling rate will also get decreased. That's why we say that as non-cyclic way of creating the cooling effect. So there are cyclic way of cooling effect. Cyclic way is basically the any kind of device, right, which can be operated in a cyclic way utilizing the refrigerant. So the working substance, right, that we are using in these cycles are called refrigerant for cooling the for producing the cooling. But in the case of engine, we were using the fuel. Here it is called refrigerant. So second is, as I said, that these are the work consuming devices. So work consuming devices will be requiring the work. So that work need to be supplied from some external source. That external source may be a motor, right, which you are operating, which is directly coupled with the compressor, because compressor is needed in order to make the flow to happen in that device. And mostly in domestic refrigerator, we use the compressor. Smaller size compressor will be there, and after that, it will be making the flow of refrigerant that is actually filled in the piping system to happen in the entire circuit. So reversed heat engine, when we say about reverse heat engine, it is a heat engine in which all the processes are reversible, but they are operating in a reverse way. That means they are now acting like work consuming device. So work is getting in the cycle, and because of that, heat transfer is taking place from low temperature side, that is T2, to the high temperature side. So this is the way by which it will be operating with, but this is still operating on the Carnot cycle. So still it's not bothering about basically the type of the working fluid that you are going to use with. So we can say that for there are two kind of devices. Those are known as work consuming device that we studied or we discussed. That is heat pump and refrigerator. So heat pump purpose is to create the temperature in a vicinity higher than the temperature of surroundings. In the case of winters, when outside temperature is lower and we want to create high temperature within the close vicinity, we can utilize the heat pump. So in the case of heat pump, usually we say that desired effect is your basically heating. So we can say Q1, and this is the work input. So work input is Q1 minus Q2, and that can be written in terms of temperature. This is the actual coefficient of performance. When you write a reversible over this, then these all Q1, Q2 will be replaced by just simply temperatures. And for refrigerator, we can say that Q2 by W, this is actual coefficient of performance of refrigerator, which is a function of heat. So when you are talking about heat, in that case, depending on the type of working substance that is called refrigerant, your heat capacity will be changing, right? If you are using water as a working substance, if you are using ammonia as a working substance, if you are using R134A, right? There are different kind of refrigerant that can be utilized with to produce the cooling effect. So if you keep on changing the refrigerant, the amount of heat transfer will also get changed. In actual case, if we consider the reversible case, right, or theoretical case, in that case, it will not be bothering about the type of refrigerant to be used. It will be only bothering about the lowest possible temperature and highest possible temperature of the cycle. So it will be function of only on temperatures. So when we talk about the reversed Carnot cycle, so reversed Carnot cycle is something, right, which operates in a reverse way, right, reverse way compared to its earlier case. So in reverse Carnot cycle, if we look at the setup, so setup will be required, right, one compressor is needed, right. So process start from the compression. So 1 to 2 is your compression process, and usually we say that compression process is isentropic, right, irreversible adiabatic process. Then process 2 to 3 your condensation, right, where because we actually in this case when we talk about the refrigeration cycle, we never look for any kind of process which is increasing the temperature within it. So we need to reduce that. So for that purpose, condenser is provided over here. So the moment some slight temperature rise has taken place after the compression of the refrigerant over here, the temperature will get reduced in the condenser. Then we'll come to the expansion valve where expansion will take place. So expander will produce some work, right? Because usually in expansion we get some work. So WE, and then finally, so what expander will do? So it will expand the refrigerant at faster rate so that the final pressure at which it is coming out from the expander is having lower pressure compared to the pressure of the surroundings. Because of that, temperature of the refrigerant Y which is coming from the expander is lower than the temperature of the surroundings. So there will be heat flow from the surroundings. So when heat is coming from the surrounding will be feeling like cooling effect. So that is called evaporation process. So it will come in. So as this is the liquid, so it will absorb the heat from the surrounding. It will get converted to the again vapor form. Then cycle repeats. Like that it will go. So if we consider right working fluid of this as a refrigerant, if we are saying as a refrigerant and it is operating on a reverse Carnot cycle, then we can say that refrigerant is first compressed. It is getting compressed, right? It is in liquid form. It is vapor form here and is getting compressed reversibly adiabatically. Always it is isentropic process. where work input per kilogram of refrigerant is given as WC. Then it is condensed reversibly, right, in the process 2 to 3, where heat rejection is taking place, right, Q1. So this is direction is not mentioned, so we can mention the direction over here for the heat rejection. So heat rejection always shows outward direction and heat addition shows inward direction. So here heat rejection is taking place, and finally it is undergoing expansion. So refrigerant then expands reversibly adiabatic in the process 3 to 4, where work output is WE, and finally it absorbs heat Q2 reversibly by evaporation from the surrounding, and then process repeats. So if we represent this entire setup, right, entire all these processes over the temperature versus entropy, we can represent over here as we are considering the reverse Carnot cycle. So Carnot cycle definitely will have two constant temperature processes and two asymptotic processes, and both of those two constant temperature processes are basically heat interactions. So heat addition at constant temperature, heat rejection also will follow the constant temperature, and two asymptotic, one compression, and there is expansion. So we can represent that over here. So 1 to 2 your compression, 2 to 3 your heat rejection, and finally 3 to 4 is expansion, and 4 to 1 is your heat addition, right? So heat addition from the surroundings you are taking in. And so we can say that initial pressure is P1 and final pressure is P2. And so we can say the lowest temperature is T2 and highest temperature is your, sorry, T1 is the lowest and T2 is the highest, because from this comparison we can say. So from here we can find out the amount of heat to be removed and amount of heat to be supplied, and how much amount of work it is getting produced. In most of the cases, right, in this case the expander will produce sufficient amount of work which is just required to run the compression, right? We usually assume that assumption. So now if we are going to write the equation, right, based on this, by applying the concept of steady flow energy equation, because open system, right, most of the case we consider all the devices are open system. So we can say the heat rejection, so from this we can say heat rejection is T1, and change in entropy, because it is an isothermal process. So we can say T1 S2 minus S3, and we can say here T2 S1 minus S4. So Q2 is equal to T2 S4 minus S4. So we can say W net is equal to WC minus WE. So we can get Q1 minus Q2, that is equal to T1 minus T2 S1 minus S4. So this is your net work. Net work is not net work actually output. It is not going to generate the work. Keep in mind, it is the work requirement. It is the work requirement basically. So P1 minus P2 is equal to T1 minus T2 S1 minus S4, where T1 is the temperature of heat rejection and T2 is the temperature of heat absorption, right? So we can say the coefficient of performance of this reversed Carnot cycle is given as the desired effect is our cooling, and where you are creating the cooling, you are creating the cooling at the base, where heat absorption from the surrounding is Q2 divided by the work input. So W net, so we can write T2 divided by T1 minus T2. This is not a coefficient of performance of this reversed Carnot cycle. So this is in the case of refrigerator. If we use the same thing for the heat pump, we can write the equation in this way: Q1 divided by W net. So this is T1 divided by T1 minus T2. So like that you can relate based on the reversed Carnot cycle. So if we go for the next, that is called Vapour Compression Refrigeration Cycle. So this is also a cycle which works on the same concept of reversed Carnot cycle. So here if you look at the components are the same, right? That is one compressor over here, then followed by the condenser, then your low pressure throttle valve or expansion valve, and then evaporator. So keep in mind, in the case of actual vapor power cycle, usually we never use the expansion engine, because power recovery from this particularly vapor compression application cycle will be very small, and when you are going to use the expander in this case, the cost wise it will not be cost effective. So in order to reduce the cost to the optimum level, we use the throttle valve or expansion valve. So throttling process, so throttling process is something where the gases or any liquid which is coming in will go all of a sudden in expansion. So all of a sudden expansion over a shorter length of span. So there will be a drastic change in pressure, or you can say significant change in pressure, but there will be very less change in temperature. You can see the enthalpy may be treated as constant while pressure will reduce significantly. So for that purpose, we use the expansion valve here, and this is your compressor and condenser and finally evaporator. So after the expansion, obviously your pressure will be at the lower side compared to the atmospheric pressure, and because of the temperature will be a lower side compared to the atmospheric temperature, and due to which heat will inflow into the evaporator and you will get the cooling effect. You will get the cooling effect only here. So if we are saying that what is the capacity of this plant, capacity of this plant will be determined by the point 1 and 4. You need to consider these points 1 and 4. So if you take the enthalpy differences right between 1 and 4, that will determine the cooling effect, how much cooling you are going to create with, uh, because of all these processes which are happening in this. So these are the total four parts of this, four components, and based on these four components, four processes, we can define 1, 2, 2, 3, and 3, 4. Now thing is that in most of the cases, our requirement is that the entry to the compressor should always be a dry saturated vapor. If dry saturated vapor we need, why dry saturated vapor? Because if it is having any moisture content in it, it will be causing lot of lubrication issues in the compressor. We look at the compressor, it is a reciprocating kind of compressor which is having piston and cylinder. So between the piston rings as well as over here, lubricating oil we are utilizing with in order to make the efficient operation of it. So if any water droplet is coming along with the vapor, right, we can say it is a wet vapor. In that case, those water particles will stick over the surface, which will wash away the liquid oil from the surface, which will create a lot of wear and tear to the surface, and function will not be smooth. A lot of vibration issues may be created. Another issue is that they may corrode the surface, right? They may have corrosion effects over the cylinder head. So longevity of the component will also get reduced. So our main purpose always we ascertain that the entry to the compressor should always be a dry saturated vapor. But in practical scenario, as we cannot 100% ascertain that it will be a dry vapor, sometime it may be a mixture, sometime it may still be a too much weight, but we need to control it. So for that, controlling devices need to be attached somewhere in between. That means we already know the three types of calorimeters that can be utilized with to find out what is the quality of steam which is coming out of the evaporator, so that we will have information in advance to take any kind of precautionary measure to make the heat flow more in the evaporator to convert the steam or vapor which is coming out from here into the dry vapor. But desirable is dry vapor always. And immediately after the compression, so entire vapor will be slightly superheated. If it's a dry saturated, if you are compressing it, it will become superheated because pressure rises, and because of that it will go to the second stage, that is called superheated stage, immediately to the right side of the vapor dome. If it is a two-phase zone, then finally it can hardly reach the dry saturated state. It is a two-way, then finally come to the certain higher dryness fraction value, right? Higher dryness fraction value after the compression. So if it is a two weight, in that case, it is very difficult for us to manage with the here, right? Even though it is beneficial, the moment is coming from the compressor, right? We can be requiring very lesser amount of heat to be removed from it to reconvert back it to the liquid, but the overall cooling effect will get reduced because we will not get the desired, compression within the compressor. So that we need to ascertain. So then after that, the process is similar, expansion, then evaporator and cycle continues. So if we draw this over the properties diagram, we can draw three types of diagrams over here: pressure versus volume, specific volume, temperature versus entropy, and enthalpy versus entropy. So one by one we'll see. So this is the pressure versus volume. This is usually follows this kind of vapor dome. So as I mentioned that there are three cases. which may occur if it is a dry saturated steam or wet steam or two wet steam. One more line you can draw in between. Two wet means it is having dryness fraction very low, right? It is much closer to the liquid line, which is on the left side of it. So here in this case, we are just considering two cases, two wet steam and dry steam. So dry state is one and wet state is one. So if you are just starting from one, hardly you can go to the dry saturated condition, which is here over vapor dome. This is a vapor dome. It can go up to the 2 dash, which is just dry saturated vapor. And if you are starting with the dry saturated vapor, definitely you will go to the superheated vapor, which is much desirable, right, in this vapor compression refrigeration plant. And this process, either 1 dash to 2 dash or 1 dash 1 to 2, this is reversible adiabatic process, right? Reversible adiabatic compression in the plant. So after that, our main motto is that we have got highest possible pressure, right, which is basically required. So highest possible pressure of the cycle. And after that, condenser, what it will do, it will reduce the temperature. So condenser, it will take away the heat and it will cool the vapors. A two-way stage to reconvert back it to the liquid form. So it is a refrigerated vapor, right? So it is a superheated vapor. So it is getting cooled from 2 to 3 and finally you are reaching just at the liquid line, saturated liquid line. So final state is your saturated liquid. So if it is 100% effective condenser, if effectiveness is 100%, we can get this stage that is called the liquid. But if it is not it is ineffective, right, maybe 90% efficiency, in that case we will not be able to reach here, then some cooling also required to ascertain that the entry to the expander should be a liquid. Now, once we reach at the 3, then your process start reversible adiabatic expansion right in the expander. So expander is nothing, not expander, expansion valve or throttle valve. And throttling is basically an irreversible process. We cannot reverse the direction. So throttling is a sudden expansion of the gases. So gases will go a sudden expansion in a very shorter length of the valve. So all of a sudden your pressure will reduce drastically, but there will be very lesser change in the enthalpy. So enthalpy can be treated as constant during this process, right? As this is an irreversible process, we cannot represent this on the property diagram. So the 3 and 4 points just will be connected by the dotted line. Then finally, as at point 4 temperature of the liquid refrigerant, because after the condenser itself it is a liquid, so after expansion it is a liquid refrigerant is lower than the temperature of the surrounding. So in the evaporator, the moment it enters into the evaporator, your evaporation process start. That means it will absorb the heat from the surroundings. And finally, by absorbing the heat, the liquid refrigerant get reconvert to the vapor. Liquid refrigerant means vapor refrigerant, and finally cycle repeats. Like that process will start. So this is the pressure versus volume. Same thing you can represent over the temperature versus entropy. Right here, isentropic lines are vertical lines. So 1 to 2 is compression, 2 to 3 condensation. Right, so condensation and evaporation, these both processes are basically phase change processes, and we know from the definition of phase change process, both usually occurs at constant pressure and temperature condition, right? Constant temperature and constant pressure condition. But as here heat interactions are involving, so obviously temperature will change, right? So we are going from superheated to the subcooled liquid, right? But while pressure is constant, so P2 and P1 remains constant. Otherwise, these are the horizontal lines, right? Even on pressure versus volume and temperature versus entropy, and this enthalpy. If you draw this over the HS diagram, right? I explained this as a Morley diagram there. So vapor dome will be looking like this, and these are the constant pressure lines, right? Usually we draw like this, constant pressure lines. So we can start with the 1 to 2 or 1 to 2 dash, 3 and 4. So here enthalpy is constant. So horizontal dotted line we need to draw. So 3 to 4 is your throttling process. So like that you can represent all the processes over the diagram. So now what is our task is to get the mathematical equations, right, for all these processes, how much amount of work is required in the compression, and how much is the throttling thing, and how much is the condensation heat transfer, and how much is the evaporation, or we can say cooling effect. So this is the cooling effect, right, that is called Q2, and this is your Q1 which is going out. So if we represent the same thing over the pressure versus enthalpy chart, this is a pH chart. So if we draw our pH chart, so this is your vapor dome, you can say saturation line. This side is the liquid and this side is the vapor. So over this is the critical point beyond which we cannot differentiate between the three phases. So all these dryness fraction lines will originate from the critical point. And this is the constant temperature lines. You just look at these are the constant temperature lines. So T1, T2, T3, and this is the liquid side. This is the liquid side, and this line is also going as ISO. What is the temperature line? And this is the constant entropy lines. Look at S is equal to constant. There will be another dotted line somewhere in here that is called constant specific volume line. So this side is dryness fraction is 100%, and this side is the dryness fraction is 0, right? That is called liquid, vapor, and liquid, and this is called vapor, dry vapor. So everything will happen in between, in between. So sometimes this chart is very useful. Like in Mollier chart, as I said, that is a very larger diagram, a larger size chart where easily you can locate the point and you can get the property values. Similarly, this is also larger size chart, right? Where easily you can locate the point by knowing any two properties, either pressure, temperature, or pressure enthalpy, or pressure entropy. Any two parameters should be known. You can locate the point and corresponding parameters can be read out of it. So here also you look at these are the two constant pressure and temperature line. These are basically phase change process line. You look at here, this horizontal line is your phase change process line. So this is your condensation usually, and this is your evaporation, right? Evaporation. This is your condensation for any kind of process. So in between you can draw the compression and expansion by dotted line. So if you expand it, you can draw like this. So this is your condensation. This is your evaporation. So process start from 1 to 2. This is the constant entropy line. Look at the constant entropy line. These are the inclined line, inclined curved line. So we have drawn from 1 to 2 is a inclined line. This is your compression process. And then after the condensation, then expansion is a constant, not is a constant enthalpy line. So vertically, right, 3 to 4 by dotted line, and 4 to 1 again concentration process or heat absorption process. So we can represent the same process, right, refrigeration process over the PS chart by using this kind of diagram. So now consider first process that is called isentropic compression. So it's the isentropic compression. If we apply the steady flow energy equation for the compression process where there is no heat involved, right? There is no inlet and outlet conditions are mentioned. So potential energy terms are also zero. Only there will be work input that we are getting in. There is no velocity terms are involved. So kinetic energy term is also zero. So if you are going to write the equation, you'll be writing like H1 is equal to H2 and minus WC. That is currently work required for the compression. So we can say the work required for the compression is basically H2 minus H1. Simply you can write so H1 plus WC is equal to H2, or you can write H1 is equal to H2 minus WC. Minus we will be utilizing because negative sign will come for the negative work. That's why that term will be coming this side. So negative will, if you take this side, to in order to make it is a positive, so we can write WC is equal to H2 minus H1 kilojoule per kilogram. This is the work required to run the compression. Similarly, for condensation, it is a constant pressure heat rejection process. So we can say H2 is equal to H2 is coming, and finally what is happening? Heat is getting rejected, and finally H3 you are getting. So Q1 plus H3, so we can get the amount of heat which is getting rejected, H2 minus H3 kilojoule per kilogram. And for expansion valve, it's a constant enthalpy process. So H3 is equal to H4. So we can see HFP2 is equal to HFP1 is equal to plus X4 HFGP2. Because H3 you already know, because the entry to the expansion is basically your liquid. But after the expansion, if it is changing slightly, if temperature is changing also, we can find out the dryness fraction of that by using this equation HF1 X4 HFGP2. So we can write X4 out of this, that is the dryness fraction. And evaporator, here you are getting in heat. So what is entering? Your H4 is entering, and in that your heat is getting add up, and finally you are getting the H1, right? So this is called H4 plus, it's not equal, H4 plus Q2, this is coming in is equal to H1. So you can say Q2 is equal to H1 minus H4 closed loop per program. This is known as refrigerating effect, or we can say cooling effect. So we can say coefficient of performance is equal to cooling effect. This is a desired effect divided by the work input. What work input? To the compressor. So we can easily define the coefficient of performance of this vapor compression refrigeration. So if we say that W is the mass flow rate of refrigerant in kilogram per second, so we can convert all these terms into the kilowatt by multiplying with the mass flow rate. So as we are saying this as a cooling effect, right? H1 minus H4 is your refrigerating effect. So we can multiply with the mass flow rate in order to convert that into kilojoule per second. So we can write W into H1 minus H4 into 3600 kilojoule per hour. So this is basically known as the refrigerating effect, or you can say this is the amount of heat which is getting absorbed from the space where we are wanting the cooling effect. So this much is enough for today. Rest of the things we will discuss in the next class.